try my voice and how loud I can get up. Because I don't know how long it will take. I tried this morning in the one-on-one class. First 15 minutes I just yelled at the top of the voice. I will do that now. So we know that this is going to be the rotation energy part. This is going to be the vibration energy part. And we're going to be adding these two and get the total energy. And we know how to do this individually. We know how to do this individually. And all we're doing now is putting them together and then saying that the set of levels here is just this ladder of states that we're going to give. So now, once you have this and you start looking at transitions, earlier we said this V0 to V1 is fundamental. V1 to V2 is a hot band. Well, now you can't say that because you have to tell me it's V0 to V1, but J something to J something. You got to add on this qualification of the J state also before you start giving me these transitions. Now let's see what happens when you do that. Something very interesting will come up. Just go back to the selection rule for delta J. When you did microwave spectroscopy, what are the selection rules there? Plus minus 1 as given to us by quantum mechanics. Am I loud enough at the back? You know? Oh, good. Because I can be a politician. So, delta J equals plus minus 1. But then we said plus 1 is okay, but minus 1. Okay, your question, I did not stop it anywhere. I did not stop it at J equals 100 or 101. The molecules is in V equal to 0 and I am simply adding on the rotation energies to that. Then what would happen is this guy would keep on rising and at this point it will be J100, maybe 99, J100, 101, 102 and so on. So essentially it means that there is a molecule with a lot of energy in it. But the energy is partitioned as small amounts of vibration energy and large amounts of rotation energy. This guy out here has V equal to 1, meaning it's got a large amount of vibration energy in it, but very little rotation energy. So there could be a point which he pointed out, something like a degenerate state. Two molecules having the same energy. But if you go and partition them out, you will find there is this with large rotation, very little vibration. Total energy is nearly the same, but a large vibration and very little rotation. So the rotation is not stopped here. So it could just keep going on and on and on. Now, if I ask you to calculate the population in a given level, why am I shouting? So if you want to have this large population, if I ask you to calculate the population in a given level, what should you do? Earlier we said e power minus E over kt, and what was E? B to J plus 1 minus Z. Okay. Now when I said calculate the population at the rotation level, what did you do? E into vibration divided by kt. But now when I ask you to calculate the population, what would you do? You really have to calculate the population in a level that has been labeled with V and J. So you must calculate the energy of the level first using this seemingly long equation. By taking this part and taking this part, you calculate the energy and then you calculate the population in that level. So now it's not just a calculation of population in a given vibration level or a given rotational level, it's a calculation of population in a given vibrational rotational level, which is now labeled with a certain V and a certain J. So if you will, you can sort of look at the molecules that are being moving around in this container, each of them having two labels on them. One label tells you what is the vibration energy present in them, and one label tells you what is the rotation energy present in them. If you know these two, you add them up, you get the total energy. And as we just pointed out, there could be two molecules with the same total energy but with different labels. So which means
the partitioning of the energy could be different. Large rotations, small vibrations, or large vibration and small rotations. But that would depend essentially on what are the labels the molecule carries. What's the B level, what's the J level. Okay. Yeah.
Let's say that we fix a B value, say is equal to 0, then there will be some J such that the energy level to the back proportion like we saw in the rotation part. Similarly, when we increase a B value, then the level at which the rotational level will reach the highest energy will be lower than the previous base.
Don't think I saw it. I'm starting here and I'm going up.
So it is happening because of the rotational energy part.
Yeah.
So but then there will be some J level
Yeah.
such that minus B into J plus 1 the whole square will be greater than the B into J plus 1. So my energy level will be lower after that.
You're talking about very large J's and the effects of centrifugal distortion and all that.
And then similarly when we increase B,
But that is going to happen at such large J's that you probably won't have population in them to even speak about. Because as you keep this, as this state becomes larger and larger and larger, the problem is this state is getting larger and larger and larger and subtracting something away, so the state tends to come back. If you want to plot this, there is a square dependence, and therefore it will have maximum minimum net function. But then, this number is so small that for that to happen, it can be a theoretical possibility, but you will not have population. It will probably happen at some J's out here and to come back.
so when we increase a B value, then also there is one minus omega like CB plus half.
Yeah.
So for example for B is equal to 0 when J stacking is happening here, for B is equal to 1 J stacking will decrease.
The J stacking will start from here. When B equal to 0, the J stacking starts from here and goes on. When B equal to 1, J0 starts from here and then J stacking goes on. There may be some J levels, some energy levels corresponding to B equal to 1, J equal to 5, which will probably have a lower energy than B equal to 0, J equal to 120 or something. It's possible. That because this guy will keep going up and this guy starts off from here. Therefore, you will find B equal to 0, J equal to 0. Will probably have less energy than B equals 1, J equal to 0. May have less energy than B equal to 0, J equals 200. It's quite possible. Because this level will just keep going on. And of course, as it keeps going further and further, the problem gets complicated because even this term is not enough. I have to put another term and another term and so on. And things get really messy at that point in time. So we will keep it simple, we just look at these two terms. And in fact, what we are now going to say is, well, the D is so small, so to begin with, I will simply even get rid of this. We will come back to it later. So we already have enough complication. So we will say, we will remove the D part, and we will simply use this term and the rotational term and stack up those levels. Because the D has a value which is something like 3 to 4 orders of magnitude smaller than B. In fact, in the exam question that I gave you, where I asked you for, I gave an equation, and then I said calculate the, see whether it is consistent with the vibrational data. I was told that you got a confusion as to what units, those 10.45 and I deliberately did not give it because we have seen earlier that equation will either be in hertz or it will be in centimeter inverse. The B value will be in centimeter inverse because it is divided by a C, and if it is in centimeter inverse, what's the B values typically like? 2, 3, 5 and so on. That first leading term at 10.4, so it essentially meant that B would have to be 10.4. But if B is 10.4, it can't be hertz. It has to be wave numbers. So that's the reason why the units were deliberately left out. And you have to decide whether it was hertz or centimeter inverse. So Ramesh was telling me that some people wanted the units. I said that's deliberately left out so that they could figure out what units they have to be. Because we had discussed in class that the units there will either be in hertz or will be in centimeter inverse. With a number like 10, it would have to be in centimeter inverse and not hertz. Okay, let's get back to this and let's see something. Yeah, we were looking at that selection rule. We said delta J equal to plus 1 is meaningful, and we said delta J equal to minus 1 is not meaningful, because delta J is going to be J prime minus J double prime, and if J prime minus J double prime is minus 1, what does that mean? That the upper state quantum number is lower than the lower state quantum number. And in pure rotation spectroscopy over here, the upper state J can never be smaller than the lower state J. We saw that at that point in time. We said, therefore, delta J equal to minus 1 is meaningless, and therefore, we will not even worry about it. As far as microwave spectroscopy is concerned, as far as pure rotation spectroscopy is concerned, delta J equal to plus 1 is all that we need to look at. But now see what happens. I'll just draw a few levels, we won't draw many. And let me assume there's an axis cut over here. So that now we go to V equal to 1, J equal to 0. And that is J equal to 1, and then J equal to 2. And all these are for V equal to 1 level. And all these are for V equal to 0 level. And we know how to calculate now the energy of each of these levels. That is simply the vibration energy superimposed onto a rotational part. Vibration energy superimposed with the rotation energy on top of that. Now the molecule makes a transition. We simply can't say it's just a V to V, V0 to V1 transition, which we call as a fundamental. Now we have to say the molecule is making a transition from V0, J0 to V1, J something. We have to give both labels, because we just said the molecules now are moving around with two labels on them. They are moving around with the labels V, and they are moving around with the label J. And therefore any transition from one level to another has to be qualified with the corresponding vibration and the rotation parameters the molecule is actually carrying, the rotation quantum number the molecule is carrying. Selection rules delta V equals plus 1. That's always going to be true as far as the molecule is harmonic. If it is anharmonic, plus 1, plus 2, plus minus 1, plus minus 2, all these are allowed. So going from here to here is quantum mechanically allowed, provided that vibration and torsional has a change in dipole moment with respect to vibration. These are necessary conditions, and we will forever assume that if I tell you the molecule is making a jump from V0 to V1, it means the resonance condition is met, it means the molecule has a change in dipole moment during a transition. And on top of that, I am now telling you that V0 to V1 satisfies my delta V equals plus minus 1 selection rule. Yeah.
So in this situation, we can't consider CO2 as having any rotation never because it doesn't have a permanent dipole.
CO2 has no permanent dipole. It has rotational levels. It won't make transitions. It won't make transitions. It will have its rotational levels. It won't make transitions. Nobody deprives the carbon dioxide molecule of having rotational levels. It's the birthright of carbon dioxide to have rotational levels. It just won't make transitions.
Does that mean V0, J0 to V0, J1, this transition will be prohibited?
Will be?
It will not take place.
Why?
Then V is not equal to plus 1.
I was just going to start the argument, but now that you put it, let me make that transition here. What is this molecule doing? It's going from V0, J0 to V1, J1. What is delta V? 1. What is delta J? Therefore, I have obeyed both the selection rules that I have been trying towards so far. Namely, a vibration transition is allowed provided the selection rule is delta V equals plus 1. In that transition which I just showed, delta V is equal to plus 1. What about delta J? It's also plus 1. Therefore, I have obeyed both the vibration selection rule and I have obeyed the rotation selection rule. Therefore, there is nothing that tells me that this reaction cannot, or this transition cannot occur. This transition will occur. Because I am going from V0, J0 to V1, J1. Delta V is plus 1, delta J is also plus 1. Meaning V prime minus V double prime is 1 J prime minus J double prime is 1, where the prime is the upper state, double prime is the lower state. Now if I want to, let us say, go from V0 to J0, what happens now? V0, J0 to V1, J0. What's the selection on delta V now? Still plus 1. But what about delta J? 0. Is 0 allowed? No. And therefore you will find that V0 to J0 transition is not going to be allowed. The selection rule on J that you learned in pure rotation spectroscopy is still valid when you do transition from one set of rotation levels to another set of rotation levels belonging to a different vibration level. So I still have to respect delta V equal to plus minus 1 in some sort of a way, as long as the potential is harmonic. If it is anharmonic, I know I can do plus 2, plus 3 and so on. Relaxation is there. But what about rotation? No relaxation. Delta J equals plus minus 1, no relaxation. You have to obey all the time. Whether you are doing a pure rotation spectroscopy or whether you are doing vibrational rotational spectroscopy, delta J has to be plus minus 1. Where did this come from? It came from the fact that I know this wave function for this, I know the wave function for this, and all I need to do is go back and evaluate the integrals and derive the selection rules from there. So when you do that, whether it is simple rotational spectroscopy in the microwave region or whether it is a vibrational rotational transition which you see in your infrared spectra, the delta J selection rule has to be obeyed. And what's the delta J selection rule? It's plus minus 1. So when I go from V0 J0 to V1 J0, I am clearly violating the selection rule on J, and therefore the molecule cannot jump from V0 J0 to V1 J0. Not allowed. How about V0 J0 to V1 J1? Allowed. We just saw that. What is the selection rule here? Delta J plus 1. How about going from V0 J1 to V0 J1 to V1 J0? What happens now? Delta V is plus 1, still okay, but what about delta J now? Minus 1. So the very celebrated thing we were looking for, minus 1 not there, minus 1 not there, quantum mechanics told us and we can't see it. Cool, it's there. So now you see that when you do vibrational rotational spectroscopy, the delta J minus 1 which quantum mechanics have been shouting at you, saying it is possible, you now get a chance to see it because the upper state rotational quantum number can actually be lower than the rotational state quantum number. But how did you manage it? By putting a different label on V. It is V0 J1 the lower state and a V1 J0 the upper state, which means that this level is quite high, sitting up here. This level is here, but this is my upper state with a J0 label on it. This is my lower state with a J1 label on it. And therefore, it now becomes delta J equal to minus 1 transition. Something we said we just can't see in microwave spectroscopy. We can now see it in vibrational rotational spectroscopy. All that we're talking now is actually vibrational rotational spectroscopy. When you do vibrational spectroscopy, rotational spectroscopy comes with it for free. You have to see it. It will be there. In fact, when you go and record your infrared spectra in your Ken 211, right? Ken 211 lab, you get these peaks. Sometimes you can see the peaks are quite broad. Why are they broad? The molecule is making rotational transitions also along with that. So we said that 2B spacing, all that is sitting there. And that's the reason, one of the reasons why these peaks are broad. Because you're not seeing just a vibrational transition, you're actually seeing a large number of vibrational rotational transitions. Earlier we made it look like the molecule goes from V0 to V1 as if it is one line. It is not one line. The molecule is going from V0 J0 to V1 J1. And then from J1 it can go to J2, which is still delta J equals plus 1 selection rule. But B1 can also, J1 can also go to J0, which is the delta J equal to -1 selection rule. And therefore now all of a sudden, the +1 selection rule and the -1 selection rule both come into play. And therefore you will have almost twice the number of lines that you normally saw in pure rotation spectroscopy. In pure rotation spectroscopy, you saw just the delta J +1 part of the line. But now you will see delta J +1 and the delta J -1. And when you see all these transitions, naturally the peaks will be quite broad. And that's the reason why the infrared spectra that you have recorded, if you go back and look at it, they'll all be broad. If you just drop into my lab, we will show you a technique in which we kind of kill all these things, and see sharp spectra, because we want sharp spectra, we don't want all the broadness. And therefore we try to suppress all the rotations by various techniques so that we get just V0, J0 going to V1, J1 transition. That's it. We have suppressed everything else, and that is something that one can do, and that's what we do all the time for a living. But if you don't do that, what essentially you will see is this level going to this level, this level going to something else, this level going to here, a whole bunch of lines. And that basically fans out as a nice set of levels that you will see. Let me forget for the moment the delta J equals -1. We have been elated that we got to see that, but let's keep it out for a while. And just look at the delta J equal to +1 transition alone. It must be very similar to what you saw earlier, excepting so the transitions happening within these levels, they're now happening between this level and that. Now, what would you see your spacings to be? This goes to 0 goes to 1. And where does 1 go to? 2. 2 goes to 3, because I'm looking only at the delta J equals +1 part at this point in time. So 1 will go to 0, will go to 1 will go to 2, 2 will go to 3, and so on. This looks exactly like what you saw in the pure rotation spectrum, right? 0 goes to 1, 1 goes to 2, 2 goes to 3, and so on, excepting that in that case, all the J levels belong to the same vibration curve. But now, all this belongs to B equal to 0, and all this belongs to B equal to 1, but it is still 0 to 1, 0 to 1 to 2, and so on. So what do you think the spacings will be like? We saw 2B, 2B spacings over there. What will it be like in this case?
Plus the
Yeah. Let me assume for the moment that the B value in this state, so the B value was given by what? H by 8 pi square IC, and I was dependent on mu r square. And in the evaluation of B, H by 8 pi square, H is same, 8 pi square, everything is same. The only thing that's going to make a difference is I. And within I, what's the only thing that's going to make a difference? R. Whether I am in this state or whether I am in this state, what's going to happen to mu? It's the same. Only the R. What is the value of R I am talking about? Average value of R. Where the molecule is going back and forth. I am going to be talking about the average value of R. For a moment, if I assume that the average value of R in this state and the average value of R in this state is the same, I don't know whether you want to agree with me on that. Good. You don't want to agree with me. But please agree with me to begin with. We'll just make life a little simpler. If I assume to begin with that the average value of R in this case and the average value of R in this case is the same, then what happens to my B value in all these states? Oh, they are all the same. If the B value here for the B equal to 0 state and the B value for all the rotation levels in B equal to 1 state are the same, then what will be the spacings in all these levels? There's 2B, 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 again the same old stuff. And therefore, what should my spectrum look like? Provided I have thrown away the D, which I very carefully threw away much earlier, so that I can have a very easy time at 6 in the evening. So now I don't have this lines piling up or 2B, 2B spacing. Why? In the case of pure rotation spectra, I only had one B value to deal with. In the case of vibration rotation spectra, I have two values of B to deal with. But I made life simple, and I forced you to make life simple by assuming that B in this state and B in that state, let's assume they are the same. They are the same, then the problem is back to what we did earlier. So there we saw 2B, 2B spacing, whereas here, again it's going to be 2B, 2B spacing, and the spectrum looks very similar to what I had earlier. And what is selection rule that gives me this? That is J equals minus plus 1. Supposing I have this J0 transition possible, it's not possible, but supposing it were to occur, where do you think it would have occurred on the spectrum? This is 0 to 1, 0 to 2, and so on. Where do you think the 0-0 transition, if it could have occurred? It cannot. Quantum mechanics says you cannot do it. But supposing it occurred, on the spectrum, where do you think it would have occurred? Somewhere over here. It could have occurred somewhere over here. Let me just put it out there and say this is 0-0 with a big question mark saying it's not going to be there. So I have this forbidden line, which is something like my starter. That's where everything should have started. But then that line cannot be seen, and therefore it's not there. Where are all the others? They're all out here. Now go back and look at the delta J equal to -1 transition. Where will that occur? It will also be, what is the spacing there? Same old story, 2B spacing. But where will it occur? This is going to be increasing frequency, and that's going to be decreasing frequency. And you will find another set of lines will occur, and that is going to be 1 to 0, and it's going to be 2 to 1, and so on. And that is going to be my delta J -1. So suddenly you find the spectrum is not restricted to one side of it. It have a bunch of lines on this side, you have a bunch of lines on this side, and one side is basically produced by a delta J equal to a +1 selection rule. The other side, which you never saw in pure rotation spectrum,